Okay, let me give you guys another example of proportionality. So I've got a tap here. I'm going to turn the water on, and the water will come out at a constant rate, meaning a constant volume per second. The amount coming out is always the same for every second. Okay, I'm trying to fill up this cylinder here, and as time goes on, the height of the water increases. My question is, can we truly say that h here, the height of the cylinder, is proportional to the time? Okay, can we say that, or is it inversely proportional with time, or is it height is proportional to the square of the time, or is it inversely proportional to the square to inversely proportional to the square of the time? Or is it like this, t to the power of 3? Or what's the relationship between time and the height? So your gut instinct will probably tell you that it will fill up at a constant, the height grows at a constant rate. But can you truly prove it? For example, what happens if you have something like this? Suppose you have this container here, okay, and the tap is here. The water is coming down at a constant rate. So when you have a container like this, the height goes up really fast, and then it will slow down because well, if you have this container here, it will fill up really fast, and then it will slow down because as you go up, the radius gets bigger and bigger. Well, if you have this container here, suppose you have a spherical container. Hang on, let's say you have a spherical container here. The water is coming down at a constant rate. You see, this one here, you start here and then you fill it up. It will travel fast, and then will slow down. It will slow down, slow down, and then it will travel. It will speed up, speed up, speed up again. So here it would go up really fast and then slow and then fast again. This one here starts off fast and then slow, slow. But what is it for this cylinder here? What's the relationship between the height and the time? Well, to investigate, let's set up a simulation here. So let's say the water is coming out at, give it anything, say 3 meters cubed per second. Okay, this thing here, the water is coming out by quite a lot per second, but it doesn't matter. Just give it any number here. So what you're saying is that every second here, the amount that the water will fill up will be 3 meters cubed. What that means is if you have a cube like this, 1 meter, 1 meter, okay, hang on, 1 meter high. So this cube here, what this unit is saying is that every second you will fill up 3 of these 1 meter cubes. Okay. Well, it does. Well, when you set up a simulation, it doesn't matter. Let's just say 3 meters cubed per second. Okay. Let's give it a radius here. It could be anything. You can make it really big or you can make it really small, but don't make it too small because it will fill up within a second. Then we can't understand what's going on. So give it a reasonable size. Let's say 10 meters here. Okay. So the volume of a cylinder, remember, you would work out the area of a circle, and then you would drag it up for the height. So the volume of a cylinder is pi r squared is the area of a circle, and then you times h for the volume of the cylinder. Now in our simulation here, let's just say after 1 second, this amount of water will come out. So that would be 3 meters cubed, but whatever, the amount of water that will come out will be 3. Okay, so the volume, what would the height be after 1 second? Well, the volume will be pi r squared times h. What would the height be? Well, you know the radius is 10, so put a 10 into there. So it's in effect 100 pi. Like, well, basically, it would be this. H. We want to know the height of a cylinder after 1 second. So, but we know after 1 second, the amount of water that will come out will be 3. Okay, 3 whatever. So the height after 1 second. Let's make up a symbol here. H1 for 1 second. It would be 3 over pi r squared. Okay, but we know the radius is 10, so put that in. Well, so it would be 3 over 100 pi. Okay, so this is the height after 1 second, and then well, what would the height be after 2 seconds? Well, if you look at this here, hang on, let me clear this. So after, so this is 3 meters cubed here per second, and this is 10 meters. The radius is 10 meters. Now, what would happen after 2 seconds? Well, after 2 seconds, the amount of water we would fill up would be 6. Okay, after 2 seconds. But what would the height of this cylinder be after 2 seconds? Well, it would be this, pi r squared times h, and then let's give it h2 after 2 seconds. So h2 will be 6 over pi r pi r squared here. Okay, so this here will give you the, well, if you turn this into a decimal, hang on, let me clear this. It will look something like this. Okay, so after 1 second, it will look, so after 1 second, the amount of water that comes out is 3. So it will give you a height of this. Okay, after 2 seconds, the amount of water that will come out will be 6, giving you a height of this. Let's give it a symbol 2. Okay, H2. And then after 3 seconds, the amount of water that comes out will be 9, giving you a height of this. Now, if you turn this into a decimal, okay, get a calculator, turn it into a decimal, turn this into a decimal, turn this into a decimal, and then you come and plot a graph of time versus the height of the cylinder. It will look something like this, and then it will actually be a straight line. So therefore, you know that h is proportional to time. Because whenever you're told that h is proportional to time, you can visualize h equals kt. Okay. Well, this here is a straight line. Anytime you have a straight line, it's y equals mx plus c. Well, c here is the original here, origin. So you can forget about it. And the gradient is really the m here is like in effect a k here. So if you plot it, it will give you a straight line. Therefore, you know that the relationship between height and time, the time as time goes on it will be a proportional relationship. Okay, but then there's a better way you can do this. Hang on, let's say this was 3 meters cubed per second here, and this was 10. Okay, 10 meters. Now, you could have answered this question by doing this: 3 pi r squared times h. Okay. Now, think about this. Hang on. After 1 second, the amount of water will be 3. After 2 seconds, the amount of water that comes out will be 6. After 3 seconds, it will be 9. After 4 seconds, well, it will be 3t as t increases. Okay, so we can say that the amount of water that comes out is 3t. Okay, and then how does that? Well, look at this here. R squared equals this here. Okay, if you want to know, well, you want to let's rearrange it so that we make h a subject. So we can imagine this as being a bubble here times this bubble here. So divide both sides by this bubble here. So it will be h equals 3t over pi r squared. Okay, and then because in our situation, we've kept the radius the same. We kept the rate here the same, whatever rate is. Just we kept this number 3. We kept the rate the same. Okay, so we are only interested in the change in the time. So it's only time that's changing, not the rate and not the radius. So when you're here, you can visualize it like this. At the moment, you've got a bubble timesing a bubble here. Move this t out, so it becomes this. H equals 3 over pi r squared times t. Okay. Well, this thing here is just a number. It's just a constant. It's just a number that we don't really care about. You see, 3's a number that doesn't change. Pi's a number that doesn't change. And the radius here is a number that doesn't change in our situation here, because we've kept the radius as the same. We're just interested in the change in time, how the change in time will affect the height. So you see, this whole thing here is just a number that we don't care about. So we can just change. We can just change the name to k. Okay. So now it's just h equals kt. So whenever you have when you're here, you can actually work in reverse and say that h is directly proportional to time. You see, you're allowed to jump from here to here, because if I say to you, oh, h is directly proportional to time, then inside your mind you can jump to h equals kt. So in this case, we were here. Now we can jump to this. Okay, so to answer this question here, well, the height, in this situation here, you can say that the height is directly proportional to the time. Okay.